This will be review, should be hopefully review, of stuff that you discussed in grade 9, but we all need to be on the same page here. On the inside front cover, I've included one of these. You should all recognize this as the periodic table of the elements. If you were in my class last year and you kept your laminated colored one, that will be useful to you. If you didn't, or you weren't in my class, tough, I guess. We don't do a big lesson on the periodic table. That's largely reserved for grade 9. So I'm going to operate under the assumption that you're pretty good with the table. And if this is the first time you're seeing it, please do let me know. I've got another one that I'll be giving to you in a little bit, not today, but you've got this one on the inside front cover to reference as we go, which you will probably need today. Okay, chemistry introduction. There's a word missing here. The word that's missing here is all. All matter is made of what? It's the word that goes in the blank. Yeah. All matter is made of atoms. There are other words that you could put in here that are smaller than that, but atoms is the distinguishing unit that we go with. Like, there are things that make up atoms. You could talk about protons, neutrons, and electrons, which we're going to in a second. But when we talk about matter, what we want the reason we talk about it being made of atoms, even though there are smaller bits, is that an atom is actually the smallest unit of an element that still has the same chemical properties of that element. So the atom's as small as you can get and still have the things that are found on this table. Hydrogen, lithium, beryllium, boron, carbon, and they all act the same way. Anything smaller, you still get particles, these particles, and there are smaller particles yet that make up these ones. But they don't have the properties anymore that these guys do. So atom's the smallest unit of an element that has the same chemical properties of that element. Atoms are made up of 3 subatomic particles that I've got listed for you here. There's protons, there's neutrons, and there's electrons. What's a proton? What do you remember? Class bonding would have helped. So what is starting later in the day? We give everyone a bit of a nap time. What's a proton? Tell me everything you know about protons. Anybody. Or I'll start pulling names. Yes, Imparis. You betcha. Protons are positively charged. Why that is complicated. What else can you tell me about a proton? Yes, sir. Imparis, go again. It's found in the nucleus. So if you recall, atoms are made up of a nucleus. Let's draw a nucleus. And then somewhere in the cloud outside, you've got another particle that I will denote this way. And in that nucleus, you've got a bunch of positively charged things. It's not the only thing you've got in there. And these positively charged things are the protons.
Please excuse this interruption. Ms. Erickson, can you contact the office?
What else can you tell me about protons? There's something special about protons that is more special than the neutrons or the electrons. The amount of protons tells us something. What does it tell you? What do you remember? Number, do you know anything about protons? I don't believe you. You're just digging in because I didn't give you a nothing block. It's true. You don't have to be the only one. It's true. Yes, sir. Michael. Sorry? Almost. Almost. It's equal to something about the atom. Yeah, Imparis again. Sorry? Yeah, it's equal to the atomic number. So this guy right here tells you the number of protons that an atom has. And if you look, the way we on the periodic table is that they go up by atomic number. Something you would have looked at last year in Science 9. And so an increase, like as the protons go up, the element changes. The number of protons you have defines the atom that you have. Protons have a mass. Does anyone remember what that mass is? Protons are too small to be weighed normally. You can't put a single proton on the scale. So we define them to have a particular mass. Does anyone know what that is? Do you remember? Did your science teacher teach you these things? Okay. Protons have a mass of 1. They're defined to have a mass of 1. 1 atomic mass unit is the language used there for the mass of a proton. They're too small to weigh anything, so chemists came up with a new unit. They said, oh, we'll call it the atomic mass unit. Protons are 1 because they're too small to measure any other way. Okay, neutrons. What can you tell me about a neutron? Let's start going through the list. Elijah, can you tell me anything about a neutron? You betcha. Also found in the nucleus. It's these guys right here. The ones that I didn't label before. Those guys right there. Neutrons are found in the nucleus as well. Olive, can you tell me anything about neutrons? Ooh, are they negative? You're right, they are neutrally charged based on the name. Neutrons are neutrally charged. If something is neutrally charged, the charge is what? Oh, we should go back and talk about protons for a sec. Imparis, you said that protons were positively charged. They have a positive charge value of what? Each single proton has a charge value of +1. Okay, cool. So if neutrons are neutrally charged means it has a charge value of 0. They're just hanging out there, providing no charge. So what they actually do is they provide mass. They exist to hang out there and just provide extra mass to the atom. They're equal to the atomic mass minus the atomic number. So I've got this example right here. We've got titanium. I've got the atomic number there. The atomic mass is here. This number down here at the bottom. So if I wanted to find the number of neutrons that were present, because protons have a mass unit of 1, neutrons, they're equal to the atomic mass. These guys also have a mass of 1. Mass of 1. And I'm gonna abbreviate atomic mass unit as AMU. And so if the neutrons all weigh 1 and the protons all weigh 1, then to find the number of neutrons, you just take the mass. We're going to round it. So 47.9 is going to become 48 AMUs. And then if you take away the number of protons, which is the atomic number right there, take away the 22 protons. 48 minus 22 is 26. Excuse me. You get the number of neutrons. So your average titanium is going to have 26 neutrons. Cool, that's neutrons. They just exist, they hang out, they exist to produce mass. And do some other cool stuff when things decay, but we'll talk about that later. Protons and neutrons found in the nucleus. Oh, I've got some symbols here too that I didn't include. Protons, typically we give the proton the symbol P+. Neutrons get the symbol N0. And then you've got electrons. That is how we denote an electron. And I placed it in a particular location. So electrons are E-. They're E- because electrons are how charged? Negatively charged. So they have a charge of -1. So they balance out the protons. They are found outside the nucleus, as I've drawn already. And the number of electrons is equal to the atomic number only in an atom. That is how you define an atom. An atom is defined to be neutrally charged. It's the neutrally charged version of a particular element. These guys also have a mass. It's much, much smaller than the protons and the neutrons. It's 0.0054 AMUs. Yes, you betcha. So all the mass is found, all of the mass that means anything in an atom is found in the protons and the neutrons. The electrons are too small to matter. Any of this is new, or if you've got questions while we're going, please let me know. Okay, ions. Atoms are neutrally charged, meaning they have neither positive nor negative charge. The reason an atom is neutrally charged is for this reason up here. The protons equal the electrons. There's the same amount in an atom. To become an ion, atoms either lose or gain what? What do we remember? Comparis. They have to lose or gain electrons. They don't lose or gain protons. That would be the only other way that this happens. If you lost a proton, you change your element. So since electrons are negative, if you lose an electron, the atom becomes what? Yep, becomes positive. If you take away negatives, you become positive. If you gain an electron, then the atom becomes negative. You're gaining negatives. And on the periodic table, you guys would have learned last year that this thing's broken up into the metals and the non-metals. The barrier is right here. It's this black line. Sometimes we refer to it as a staircase that goes down and it cuts the table into two. Everything to the left of the staircase is considered a metal. Everything to the right of the staircase is considered a non-metal. There's some awkward ones kind of right along the staircase that have their own name. Call them the metalloids because they're kind of like a metal. All metals lose electrons to become positive. all nonmetals gain electrons to become negative. I think there's only one exception to that rule, and that's hydrogen. Hydrogen's its own weird little beast. So we look at the periodic table. I've got two examples down there. We've got chlorine and magnesium. You would have spent a lot of time last year scouring the table for things. You're going to do that again this year. Chlorine is this guy right here. I don't know what version of the periodic table you were given last year, but on this version of the periodic table, if it just has the minus sign there, or on this side, if it just has a plus with no number, that means it's +1 or -1. So if you take a look at chlorine here, chlorine is minus, and chlorine happens to be over here with the nonmetals. So a chlorine ion is a nonmetal. It gains 1 electron. Becomes negative. If we take a look at chlorine again, chlorine's this guy right here. When chlorine becomes negative, how many electrons does it have? Yeah, Himparas. Why? Sweet, yeah. So chlorine had 17 protons. So the atom would also have 17 electrons. To become negative, you gain 1. Yeah, you betcha. It becomes negative. So let's put that down in here. It had 17 electrons. It gained 1. To give you 18 electrons. And then likewise, magnesium. Magnesium's over here in the middle. Nope, I lied. It's on the far left-hand side. Magnesium's that guy right there. Gives you a charge, or becomes charged +2. So magnesium's a metal. To get a charge of +2, what does it have to do? It's got a charge of +2. How many did it have to lose to become +2? It's got to lose 2. Because each one it loses is a charge of -1. So to gain, to get more and more positive, you have to lose more and more negative. So when it loses 2 electrons, it becomes positive. It had 12 electrons, lost 2 electrons. Now it's got 10 electrons. Okay, I have a little table here I want you to try. This guy right here. I want you to fill that thing in. I've got some elements listed here. Some of them are not listed. You have to figure out what they are. I've got atomic numbers. We've got ion charges, numbers of protons, number of electrons, number of neutrons. Based on what we did on the previous page and what you've looked at in grade 9, just review. I want you to fill out each row given the information that's present here. On your mark, say given. You discuss with the people sitting around you. If you need a hand, let me know. But I want you to try that table based on the stuff that we just talked about. This is what this table should have looked like. If this was something that you were struggling with, please let me know. Happy to assist. Compare your values with my values. If you didn't get it, finished, you do need to know how to do this stuff. And then we added the column on the left-hand side telling me whether it was an atom or an ion. Comments, questions, concerns on any part of this table. Take a look. Did I make any mistakes? Are your values the same as my values? Does anyone have any questions about how I found what I found? If this makes it better, easier to see. Okay. We good? Okay. There are no questions. Those of you who are you done checking? Can I slide this thing up? Okay. If you didn't get it finished, I want you to finish that guy for homework. And we're going to review something else that you would have looked at in grade 9. Hands up if you remember drawing Bohr models. You probably drew a lot of these. Every teacher who assigns them slightly differently. Yeah, let me see if you need to go to the washroom now. You can. Okay, that works too. The Bohr model was one of a bunch of different models you guys would have looked at last year. You would have looked at, or you should have looked at, a group of, I think it was 4 scientists. Dalton's model, and then you would have had Thomson's model, and then you would have had Rutherford's model, and then you would have had Bohr's model for an atom. Is this ringing any sort of bell? Some of you recall? Okay. The Bohr model was the last one you guys would have looked at, and it's, if we're going to be really clear, it's not totally accurate. It's got problems. And if you watch, I don't know if you guys do, I follow a lot of different scientists on various social media platforms, and you'll see stuff like how the Bohr model is just wrong, and we don't actually know what an electron is. Do we even know if it's a particle? We don't. We can't know if it's a particle at this stage, but we assume that, at least for our purposes, that it is. And even though a Bohr model is not totally accurate, it's still useful. It's got problems. Atoms don't look like this. And some Science 9 teachers talk about this, some don't. I do. I want to make it really clear that, yes, this is a model we have. It is not even remotely correct. Atoms don't circle around the nucleus like this in the real world. But this is a great way to visualize how they do actually behave. In the real world, these aren't just circles that they float around. They're actually different shapes. This inner one is a sphere. This ring is actually 4 different shapes, or 3 different shapes. It's a larger sphere and some other shapes, but some teardrop shaped objects. It doesn't actually matter what those shapes are. These rings are useful for telling us what electrons exist on what energy levels. I don't think I actually have my poster up of the weird shapes. No, I didn't put it up. So Bohr diagrams, not accurate, still useful. They are a way of visualizing atoms. And they use these rings to represent something specific about an atom. Does anyone remember what these rings are called? 2 words. The first word is named for the object, and the second word is, I don't know if that helps at all. Well, the first word is electron, because electrons are contained in these objects. Himparis, do you remember? Yes. We call them shells. And that's a useful word to use. In an electron shell, the electrons are found somewhere within that level, that shell. They're used to describe the location of electrons around an atom. They have two other names as well. Does anyone remember what else we call an electron shell? It's either one word that starts with an O, or two words that start with an E and an L. Do you remember? Number, do you remember? So far you haven't said anything. Right now it's been Imparis answering everything. No, but then Imparis took over. The sarcasm is still strong. Okay, but so they're also called orbitals. Is other language that we use to talk about these electron shells. Or we can call them energy levels. Because that's another thing they represent. The higher the shell you're in, the more energy that electron has. Each shell can hold a certain number of electrons before it's what we can consider full. Does anyone remember what these values are? You would have looked at them last year. In the first shell, how many? Well, in the first shell, we've got how many? 2. The second shell is 8. The next shell up is 8. And the next shell up is? That one's not included on here. Anyone know how the numbers go? Yeah. Almost a little bigger. 18. And these things are actually related to something on the periodic table. If I'll flip back, you don't have to. If we go back and we take a look at the periodic table, I'll zoom this thing out. In row 1, you've got hydrogen, you've got helium. There's only 2 elements there, and there was only 2 electrons in that outer shell. So this first row represents that first shell. This second row has 1, 2, 3, 4, 5, 6, 7, 8. So this second row has 8 elements in it. There's 8 electrons in that second shell. This next row has 1, 2, 3, 4, 5, 6, 7, 8. This second row represents that third shell. And then the fourth row has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. The row you're in is the shell, the maximum number of shells the element can have. Yes, Imparis. What about the bottom 2 rows? Yeah. Like this row would go 55, 56, 57, 58, 59, 60, all the way up to 71. And then it would jump back over here and continue this way. Yeah, that is still true. So you'd still have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. On that particular energy level. And there's a bunch of different shapes that are contained within each energy level. So yeah, down here you'd have 32 electrons at a particular energy level, and then 32 on this bottom row as well. We loop this around like this. Well, there's a couple reasons we do it. I mean, to fit it on one page nicely, we cut out this section. And it loops around like this because if you guys recall, they're stacked in families by property. So these ones all have the same property, this column 3. Column 4 all has the same property, but if you break it here between 3 and 4 and split them, these guys, they have to fit in here based on their atomic number, but these guys don't have any properties of the ones above, but they're stacked in such a way that they have properties of what comes below them, if that makes any sense. These guys from 93 to 103, those guys don't exist in nature. We made those in the lab. Actually, 93 to 118. Everything past 92 doesn't show up on its own in nature. So the shell you have, oh yeah, let me, yeah. The shell you're in is the maximum number of shells comes from the row that element is found in. So these are the row on the periodic table. Periodic table. Tells you what row you're in. So when we draw these Bohr diagrams, the way that we visualize these things is we draw the number of shells and then we fill those shells up. So when you're filling the shells with electrons, now every science teacher is going to teach this a different way. This is the way that I recommend doing it. You start at the top, wherever that top is, or whatever shell it is rather, and then you move. Typically, not always. Sometimes it's useful to go the other way, but typically you move clockwise. So you go the same direction the clock would, adding electrons like points on a compass, one at a time. I'll add this in here, one at a time. And you go around twice. So once a shell is half full, so one at each point, at that point you begin to pair the electrons. You go around a second time. Okay, when you're ready, flip the page. So steps for drawing a Bohr diagram. This is what I want to see when you guys draw me Bohr diagrams. When you're drawing a Bohr diagram for an atom, I want to see the protons and the neutrons labeled at the center of your Bohr diagram. So I know every science teacher is different. Perhaps your science teacher last year didn't care about that. I want to see it. So you're going to find how many protons you have. You're going to find how many neutrons you have. And that's going to represent the nucleus of the atom. It's going to go at the center of your diagram. Together, this is going to make up the nucleus. You're going to determine the number of electrons that the atom or the ion has, and you're going to start filling up the energy levels, or the energy shells. If you remember, it goes 2, 8, 8, 18. You're not going to have to draw. I will not make you draw Bohr diagrams for anything bigger than 20. So you'll never have to actually fill this outer shell. You'll do nothing bigger than 20 electrons. Past that, things just start to get ridiculous. Once the shell's half full, you stop pairing. There's an extra step for an ion. If what I've given you is an ion to draw, there's going to be a different number of protons as electrons. So the extra step for an ion is once you've got an ion, you're going to put brackets around the diagram, and you're going to put the ion charge outside the top right corner. And this is going to be the last thing we do today. So if I've got hydrogen, I've got lithium. Let's do an atom of hydrogen first. So this is going to be referencing the periodic table a lot. The atom of hydrogen. Hydrogen is how many protons, how many neutrons. First thing we got to identify. I'll take a look. Hydrogen has an atomic number. It's all labeled right here. Hydrogen's got an atomic number of 1. It's got a mass of 1. So if it's got an atomic number of 1, that tells you how many protons there are. P plus equals 1. And if the mass is also 1, how many neutrons are there? Remember, neutrons are mass minus atomic number. So there are none. 1 minus 1 is 0. There's no neutrons in hydrogen. It's just a single proton. Okay, so then if you have an atom, in an atom, the electrons equal the protons. So if I've got 1 proton, I'm going to have 1 electron. Hydrogen is in row 1, so it's only going to have 1 shell. And I put my 1 electron up there at the top. Questions about what I've done? Okay, let's do the same thing for lithium, but I'm going to make it an ion this time. We're going to do a lithium ion. If you look, when lithium becomes an ion, lithium becomes +1. That's what it says on the periodic table. Those are the values we're going to use. Lithium becomes a +1 ion. So if it's going to be +1, what has happened to lithium to become +1? Did it gain or lose an electron? It lost. It had to have lost. If it became positive, electrons are negative, means it lost an electron. So first thing we're going to include is the number of protons, the number of neutrons. Lithium has atomic number 3. That's the number of protons. It's got a mass of 7. If I round 6.9, it rounds to 7. 7 minus 3 is? 4. So that means there's 4 neutrons. And if a lithium ion has a charge of +1, that means this ion has 2 electrons. So we're going to put the first ring, or the first energy level. In the first one, there's only space for 2, so we put them beside each other. And your lithium ion is done at this stage because it's only got 2 electrons. If it was a lithium atom, we'd have 1 more, we'd put another ring, and we'd keep going. Because we have an ion here, we put brackets around the thing, and we write the charge up in the top right-hand corner. Would anyone like me to do another example of these things? Okay. I'll do an example. So this table here, it says draw Bohr models for the following elements. These ones I want you to treat all as atoms. And so I'll do one of these. I'll do nitrogen. Nitrogen's a nice, easy one to do. I'll do this guy as an example. On the periodic table, we find nitrogen. Nitrogen is this guy right here. Has an atomic number of 7 and a mass of 14. Okay, so if it has an atomic number of 7, that means the protons are equal to 7. And if it has a mass of 14, then to find the neutrons, we take the mass, we take away the atomic number. 14 minus 7 is also 7. And if this thing is an atom, it's going to have the same number of electrons. So we can start putting those in. The first shell can only hold 2, so we put them together up here at the top. Then we add another ring. We've done 2, so we start at the top. 3, 4, 5, 6. We put 1 at each spot. And we need 7 total, so I've got 1, 2, 3, 4, 5, 6, 7. We've added 1 more and we're done. So that's the atom. I'll do one more example of an ion. Flip the page. I want you, on this page, I want you, these guys as well, drawing Bohr models for the following ions. You guys are going to do 6 of these for me here. I'll do one example of these guys. We've done lithium already. I'll do sodium, this guy down here as an example. And then the rest will be for you to play with. So sodium on the periodic table is this guy right here. It's got an atomic number of 11, an atomic mass of 23. So the atomic number of 11 tells you how many protons there are. The mass was 23, so then the neutrons are going to be the mass, 23, minus the protons. 23 minus 11 is 12. And the sodium ion is positive 1. So if it's positive 1, that means the sodium ion has lost an electron again. So that means that the sodium ion is only going to have 10 electrons. So my first shell has 2. My next shell has 3, 4, 5, 6, 7, 8, 9, 10. That's everything sodium's going to have. Because it's an ion, we put the square brackets around the thing with the charge up at the top. Questions, comments, concerns? Okay. With the time that remains, so there's 10 minutes left. I want you to do, there's 10. No, there's 10. 5 atoms, 5 ions. I want you to draw those board diagrams for me. This is the last thing I'm gonna get you to do today. On your mark, say giver. I'll put the music back on and away you go. Let me know if you need a hand. The boards are available to use if you guys would like to use them. On your mark, say go. These 10 questions, that's all I want you. I want you to get that done for homework.